So in this next section, we want to combine the ideas of spontaneity and entropy. So most spontaneous processes are exothermic in the sense that they release heat energy. And in this case, what we're looking at or what we're thinking about is processes that are chemical in nature or chemical reactions. But there are some processes that are spontaneous and endothermic, where they absorb heat energy. And here's an example of ice melting. In order to get ice to melt, if you remember, you have to add 6.01 kilojoules per mole at the same temperature. So if you have ice at 0 degrees and water at 0 degrees, we have to add 6.01 kilojoules per mole in order to get ice to turn to water. But if you go to a temperature above 0 degrees C, this will actually happen spontaneously. And the reason that this happens spontaneously is there is an increase in entropy. The molecules in water have more freedom than the molecules in ice. This additional freedom, or an increase in the number of microstates, if you will, is what is going to cause this process to overall be spontaneous, even though it is endothermic. So the take-home message of this slide, which we won't get to until the end of the chapter, is that spontaneity depends on two things. Enthalpy, which determines exothermic or endothermic, what happens to the heat of the system, and entropy, what happens to the randomness of the molecules. So let's just use some oversimplified definitions here to talk about enthalpy and entropy. Enthalpy, or delta H, okay, that you've already learned about, is the measure of heat energy in the system. Entropy is the measure of disorder of the system. And entropy has a unit of delta S. So enthalpy can be thought of, again, as heat energy. So if we want to get solid to turn to a liquid, we have to add heat energy. This has more entropy because the molecules have more disorder. Okay, they're less ordered than this, or they have more degrees of freedom, if you will. If we look at increases in entropy from a practical definition, to bring up a picture that I showed before, entropy from a very practical standpoint can be thought of as disorder. This older house is more disordered, and this newer house is more ordered. And we talked about this before as in terms of statistics. There's an infinite number of disordered, rundown houses, right? There's an infinite number of ways that this house can become disordered. The paint can chip, a ceiling tile can fall off, although it looks like it has different types of roofs in these two pictures, or whatever the case may be. But there's only one perfect way. So it's more likely to have disorder and less likely to have order. And as we all know, if you want to keep the house ordered, you have to put in physical energy, right? You have to actually fix things as they break. This is not a great definition of entropy. And thinking about it just in terms of randomness or disorder or something like this isn't perfectly correct. And in this video, which does a much better job than I can do of explaining entropy, it's thought of in terms of condensed and distributed energy. And I strongly recommend that you take the whatever it is, 10 or 12 minutes, to watch this video because I think it'll give you a more nuanced definition. Now, you may not want to do that now. You may want to play with these concepts a little bit and do some of the math and then come back and watch this video because I do think it will give you a better understanding that will help you moving forward into other classes where they discuss this same topic. Oh, I didn't want to play the video. Sorry about that. So, the second law of thermodynamics tells us that the total entropy of the system always increases over time. So things become progressively more disordered if we think of entropy in terms of disorder. For a spontaneous process, the entropy of the universe always increases. And if you look back at the way that it's described in that video, energy always becomes less condensed or more distributed. And as we talked about before, even if you have an apparent decrease in entropy, water freezing, it can still be spontaneous if there's a corresponding increase in enthalpy of the surroundings. So this is the opposite of the case we discussed where we were melting water. If we freeze water, which looks like it's causing more order, this will happen spontaneously at temperatures below 0 degrees Celsius. Put some water in your freezer and it will freeze it spontaneously. And the reason that this occurs spontaneously at temperatures below 0 degrees Celsius is because there's an increasing enthalpy of the surroundings. So we're going to look at this both mathematically and a little bit practically. I understand these ideas are a little bit vague and hard to understand, but I hope as we start to look at more examples, and then after you look at some more examples, you watch that video, it will help you to have a better nuanced understanding of what this concept entropy, thought simply as randomness or disorder, means. So what we can think about this mathematically is in terms of the Boltzmann distribution. So here we have S, and S is our term for entropy. Remember, H is our term for enthalpy, and S is our term for entropy. K is the Boltzmann distribution constant, which is just 1.38 times 10 to the minus 23 joules per K. And then we have ln W, where W is the possible number of microstates. And in a minute, we're going to look at some examples of the possible number of microstates in some very simple examples. But one thing you want to keep in the back of your head is, think about this if you had a mole of gas, how many microstates there would be. It would be a massive, massive, massive number of microstates, and this math would get overwhelming quickly. All right, so here we have a different version of this where we have delta S, where we look at the microstates final versus the microstates initial. What does all this mean? It looks like some complicated math, and we're not actually going to solve this Boltzmann distribution, K, L, N, W. Instead, what we're going to do is we're going to think about it from a theoretical perspective. The general idea here is that things can either become more ordered or less ordered based on if there are a more probable or less probable microstate. So if we think about this in terms of the house, this is the more ordered version of the house. So if the house goes from this disordered to this ordered, the change in entropy is negative. We made things less random. This is more random and this is less random. So if we fix up the house, then the change in entropy is negative. However, if we do the opposite, if we go from this nice house to this crappy house, okay, we have made the change in entropy positive because we went from very ordered to very disordered. Now we're going to try to talk about this in terms of microstates, which is, balls in a box, essentially. All right. So we have these little balls representing atoms in these two boxes. And if we look here, this is an ordered state. If we look at disordered states, where there's two of these atoms in each box, what we find is that there are 6 possibilities that we can have 2 atoms in each box, because each of these atoms has its own unique identity, here represented by colors, red, green, blue, and yellow. And there are 6 different ways to do this. So this state is less ordered or more disordered when you have 2 balls in each box. When you have all 4 of the atoms in a single box, it is more ordered. So this state has a lower entropy than this state. So if we go from this state to this state, we have increased the entropy. If you look at this from a larger perspective, there's actually 16 different ways you can represent these 4 different atoms in these 2 different boxes. Now imagine a situation where you have, a mole of atoms, 6.022 times 10 to the 23rd. In that case, you're going to have to use advanced statistics to do those types of calculations. When I say advanced, they're advanced for me, all right? They may not be super advanced for the people who are actually doing them. But I'm not real familiar with those statistics myself. So here we have all these states. There's one state where all the atoms are in the left-hand side, and one state where they're all in the right-hand side. There are 4 states where you have 3 atoms on the left and 1 on the right, and 4 states where you have 1 atom on the left and 3 on the right. There are 6 states where there's 2 atoms in each box. When you add this all together, there are 16 different possibilities of microstates for this particular system. And this is a very simple system with only 4 atoms. Now, if we look at this example, it says, in which of the following diagrams is delta S positive? In which of the following diagrams did we increase the disorder? Because when delta S is positive, it means we've increased the entropy or we've increased the disorder. Well, if we look here, having 2 atoms in these boxes, we remember that there are 6 states like this, and there's only 1 like this. So we've made this more ordered. This is 1 out of a 6 condition, and this is a 1 out of 1 condition, if you will. So this is more ordered. So therefore, we have increased the order and decreased the disorder. So delta S is negative. In this case, we have 3 and 1, and then all 4. Same thing as 2 and 1, 2 and 2 going to all 4. We have made this more ordered or decreased entropy, the randomness or disorder. In this case, we have all 4 in one box, and then we have 2 in each box. So in this example, we have actually increased the disorder, and delta S is positive. So delta S is positive when we increase the disorder of the system. Generally, we're not going to think about the entropy in terms of the Boltzmann distribution because of the advanced statistics that I mentioned before. But there are some practical ways that we are going to consider increases and decreases in entropy. And one of them is based on states of matter. So generally speaking, solids have less randomness than liquids, which have less randomness than gases. Said another way, as we go from solid to liquid to gas, entropy increases. Now, if we do the opposite, if we go from gas to liquid to solid in this direction, entropy will decrease. So, based on states of matter, we can think about changes in entropy. If we go from a solid to a gas, entropy will increase. If we go from a liquid to a solid, entropy will decrease. Another way to think about this in terms of chemical reactions is moles of gas. So if we look here, we have 2 magnesium solid plus oxygen gas yields 2 MgO solid. In this case, we have 1 mole of gas on the reactant side and no moles of gas on the product side. In this case, the entropy decreased because now this gas is part of this solid, so we have decreased the entropy, or delta S is a negative. In this case, we have KClO3 solid forming KCl and 3O2, 2 KCl and 3O2. In this case, we have no moles of gas on our reactant side and 3 moles of gas on our product side. So in this case, the entropy has increased because we went from 0 moles of gas to 3 moles of gas. Take home message: when we lose moles of gas, the entropy decreases. When we create moles of gas, the entropy increases. What about temperature and entropy? Well, temperature is looking at an increase in entropy as temperature increases. So if we look at entropy on this axis and temperature over here on this axis, what we find is as the temperature increases, even in the same state of matter, the entropy increases. But then when we change states of matter, we get a large change in the entropy without a change in temperature. This is kind of like a phase change diagram turned on its side, okay, if you will. So, generally speaking, as temperature increases, entropy increases. So if you're thinking of two gases at different temperatures, the one at the higher temperature will have increasing entropy. And we already talked about melting and boiling. All right. If you want to think about why this is, it's because if we look at T1 versus T2, even in the same state, in T1 there's a smaller distribution of kinetic energy among the molecules. At T2, there's a larger distribution of kinetic energy among the molecules. This larger distribution of energy translates into more entropy, more randomness. The energy is more spread out at the higher temperature as compared to the lower temperature. Finally, a change of state that involves dissolving something. If we have solid KCl and we turn it into aqueous K plus and Cl minus by dissolving it in water, said another way, if we dissolve KCl, the aqueous ions have more freedom and are more random than the solid KCl. So these practical aspects are what we're really going to consider in terms of entropy in this section more than the microstate stuff. The microstate stuff gives you an idea of why this is happening statistically, using a simple example of having 4 atoms in 2 different boxes. But there are much more practical aspects, including state of matter, the moles of gas on the product and reactant side, the temperature, and whether something is solid or dissolved in water. So let's look at an example where we look at which direction the change in entropy is. And I'm going to switch over to the camera here so that we can do this. So we want to decide if entropy is positive or negative. Basically, we want to find the sign on delta S. So here we have a solid melting. So we have a solid forming a liquid. A liquid has more freedom or more randomness than a solid. So in this case, delta S is positive and entropy increases. Let's look at the next one. A gas condenses. So we basically have a gas, all right, forming a liquid. So when a gas condenses to form a liquid, we've gone from something with more disorder to something with less disorder. Said another way, entropy decreases where delta S is a negative. A solid sublimes. A sublimation is going from the solid phase to the gas phase, skipping the liquid phase. In this case, this is more ordered, and this is far less ordered. So we've increased randomness, we've increased disorder, and delta S is positive. A liquid freezes. So we have a liquid forming a solid. A liquid has more disorder, and a solid has less disorder. So we've lost disorder. Said another way, delta S is a negative. Let's look at the next one, which is a bunch of reactions. It says for the following reactions, decide if the entropy is positive or negative. Decide if the change in entropy is positive or negative. So here we have 3 plus 1, or a total of 4 moles of gas. On this side, we have 2 moles of gas. So we have lost 2 moles of gas. We went from 4 moles down to 2 moles. 2 moles of gas will have less entropy than 4 moles of gas. So overall, delta S is negative because we lost moles of gas. Let's look at this one. On this side, we have 1 mole of gas. And on this side, we have 0 moles of gas. So we went from 1 mole of gas to no moles of gas. This has more randomness. This has less randomness. So again, delta S is a negative. For the last one, it says in each pair, which has greater entropy? Well, here we have phases again. We have liquid water or gaseous water? Well, the one that's a gas has more freedom and therefore more entropy. And in the next case, we have aqueous NaCl versus solid NaCl. And as we talked about before, the aqueous NaCl is the one that has more randomness, or the molecules have more freedom, or they're more disordered, or however you want to say it. So this is more of a practical aspect of what is happening to the entropy in actual things that are related to chemistry. And that's not to say the microstate stuff isn't, but again, when you're dealing with a mole of atoms, that's not something you're going to solve on a general chemistry test. In the next section, we'll look at the third law. We'll review the second law of thermodynamics, and then we'll talk about the third law of thermodynamics, and we will calculate entropy as a mathematical value in a new way.